So here I'm going to go over the practice problem for flood frequency analysis using data for the Henry's Fork River in Idaho from the period 2000 to 2015. This is only 15 or 16 years worth of data, but the procedure is the same for even larger data sets, which is something you're going to have to do in your homework. So here is the spreadsheet that I've opened. It shows 16 years of data with peak discharge in cubic feet per second. First step I'm going to do is to put these in order. I really don't care about the date. What I care about is the rank of the peak discharges, peak annual discharges. So to do that in Excel, I'm going to highlight the rows that I want to sort, and then I'm going to pick Data, Sort, and I'm going to sort actually here it says there's a box here that says my data has headers. I'm going to uncheck this because I don't have headers, and this allows me to sort by column. I want to sort by column B, which is the discharge from largest to smallest. So there you go. So I've automatically sorted the discharges from largest to smallest, and now in column C I'm going to rank them. I'm going to call that M, the rank, and I'm going to start the first largest is 1, the second largest is 2, the third largest is 3. I want to change the format. And now I'm just going to expand that range down to the bottom by grabbing hold of the little dot at the bottom of those first 3 blocks that I highlighted and dragging it down. And there you go. So there's my ranks of my discharges from the largest down to the smallest. And we can see that I've got 16 years worth of data. That's an important number to remember. So the next column here in column D, I'm going to estimate the return period in years. And I'm going to use the formula that the return period is equal to n plus 1 over the rank m. So n, remember, is 16. So this formula is going to equal to 17, always 17 for this problem set, divided by the rank, which is in cell C2. And there we go. So the largest peak discharge is always going to have an estimated return period of 1 more year than the years of data. So it's 17 years. And I'm going to, again, copy this formula all the way down. And there we have the estimated return periods for these discharges in column B. So the next step is to plot the return period on the x-axis versus the discharge on the y-axis. And remember, to do that in Excel, when I grab 2 columns and plot them, Excel is going to assume that the first column, the one on the left, is the x-axis. So in order to make that happen, I'm going to need to copy this over, and I'm just going to copy it over there. So I've copied it into cell E. So E and B are exactly the same thing. But the reason I did that is so now I can grab both of these columns like this and graph them, and it will put the return period on the x-axis and the peak discharge on the y-axis, which is what I want. So I'm going to pick a chart, a scatter plot with just dots here. And there we go. So those are my data. I'm getting there. Get rid of the title because I don't care about that. And remember that I want to graph the logarithm of the return period. So I'm going to have to change my x-axis to logarithmic. So I'm going to highlight my x-axis, and I'm going, that wasn't it, and I'm going to, I'm going to highlight my x-axis, format the axis here, and I'm going to choose a logarithmic axis. There we go. So that's my x-axis, and the next thing I want to do is fit a trend line through these. Remember, this is essentially a straight line on the logarithmic axis. To do that, I'm going to highlight my data, add a trend line, and it is going to be an a logarithmic trend line when the x-axis is logarithmic. So it's a logarithmic trend line. There you can see it's a pretty decent fit to my data. That's what I want, right? But furthermore, I want to extrapolate this beyond my data towards return periods that are much longer than this. In fact, I want to ultimately estimate the discharge for a return period of 500 years, which is actually 483 years beyond the 17 years of data that are 16 years. So I want actually, I want to forecast, as we call this, forecasting this forward 484 years. That's crazy, right? But that's what I'm going to do. And I'm also going to display the equation on the chart because it turns out that's something that I can use to make predictions accurately about the discharge at various return periods. So there's my equation. I'm just going to make it a little bigger so it's easier to see. Okay, so now I'm almost done. So now I fit a graph to my data. It looks pretty good. Remember, the idea is I want to extrapolate these data, and this extrapolation looks pretty good because these data really do fall pretty closely along this line. So I have some level of confidence that I can extrapolate it, even though extrapolating it to 500 years is a great overreach, but I'm going to do it anyway. So at this point now, I want to actually estimate the discharge for return periods of 50 years, 100 years, and 500 years. And I'm going to do that by simply plugging into this equation. This equation gives the discharge in the y-axis, or the y value is the discharge, for any x value being the return period. So for a return period of 50 years, I merely need to plug into this equation with x equal to 50. So I'm going to enter this equation into the cell B19. So it's equal to 4459.7 times the natural log of x, which is now in A19, right? That's my value of x, plus 3135.2. And there you go. So the estimate of the 50-year stream discharge is about 20,500. That should kind of make sense, by the way. Maybe we can show that here. If I show the minor grid lines, 10, 20, 30, 40, 50, it's up in here. That makes sense. It's a little bit more than 20,000. That looks right. For the 100-year stream discharge, all I need to do is copy this equation down. So 100-year stream discharge is just a little bigger at nearly 24,000. That makes sense again. That looks about the right place. And the 500-year stream peak discharge would be almost 31,000 cubic feet per second. These are all in CFS. I should probably put that there so I don't forget. Those are my estimates of the 50, 100, and 500 year peak discharges based on the analysis of these 16 years worth of data at Henry's Fork.